Hi, everyone. This lesson is going to be all about the pH scale, something you may have heard of in science classes before, but we're going to tie it back to how it relates to Regents chemistry and the definitions of Arrhenius acid and Arrhenius base. So what's frustrating about just defining an acid as something that's sour or something that produces H plus is that we can't tell just by looking at something how much H plus it has, or maybe we don't want to taste it to find out if it's sour or not. That brings us back to the quantitative chemistry that everyone loves. And when we define how acidic or how basic something is, what we're really doing is giving a reference as to what the concentration of H plus or hydronium, H3O plus ions is in solution. And in a very formal sense, if the concentration of H plus, here we're using the units of molarity, moles per liter, is greater than 1.0 times 10 to the minus 7th molar, so we have more than a certain cutoff of H plus. The more H plus you have, the more acidic you are. So you're classified as an acid if you have more than this cutoff amount of H plus. If you got anything less than that amount, you're a base. However, working with these types of numbers and very specific concentrations of H plus can be kind of cumbersome, and that's when the pH scale came around. We're going to take this exponent right here and call that cutoff number a pH of 7, which is going to divide our acids and our bases on the pH scale. Water is a key example of something that has a pH of 7, and we call that a neutral compound. And all neutral compounds have the same amount of H plus and OH minus ions. And the way we can kind of justify that is that in a reversible reaction, H2O can break apart into H plus and OH minus, so we must have the same amount of H plus and OH minus in our solution when it is neutral. If we start leaning one way or the other, so start increasing the amount of H plus we have, then we must be making our substance more acidic. So acids have more H plus than they do OH minus. So we're going to slowly start increasing H plus, and the amount of OH minus will decrease as we move down the scale. So the lower the number, the more acidic your substance is. The opposite is true for bases. If we move up the pH scale, what we're really doing is increasing the amount of OH minus ions that are around. So bases have more OH minus ions than H plus. The farther up you go, the nastier those substances are because they have more of these corrosive OH minus ions present. And what's nice about this pH scale is that it's really simple, but what's also deceptive about this scale is its simplicity. If we take a look at a couple sample substances like water and soda, it's easy to say, well, if a typical can of soda has a pH of 3 and water has a pH of 7, that's like 4 times more acidic. That's not so bad. But what we can't forget is the fact that this scale isn't just a basic little linear thing. Remember, it came from a very ugly mathematical situation up here. So because this scale is based on a mathematical function called a logarithm, every jump we make down the pH scale reflects a 10 times or a tenfold increase if we're moving down, or decrease if we're moving up in H plus concentration. So when I ask a question like how many times more acidic is a typical can of soda with a pH of 3 than distilled water with a pH of 7, what we really are asking is if I take this pH from 7 and move it down 4 pH units, every jump multiplies by 10, not adding together, multiplying. So I've got 10 times 10 times 10 times 10 for a total of 10 to the fourth, 10 times 10 times 10 times 10, or 10,000 times more acidic than our regular distilled water. So with every jump, we increase our amount of H plus if we're moving towards the more acidic side. If I take a look at a different example, by looking at what happens to the hydronium ion concentration when a solution of distilled water is swapped out for egg whites, the first thing I need to do is remember what in the world hydronium is. If you look it up on table E, you'll see that hydronium ions are just those H3O plus ions, which we can, for all intents and purposes, just swap out with the idea of H plus. So the concentration of H plus is going to increase or decrease when I move my pH from 7 to 9. Because I'm moving towards the more basic side, I'm increasing my OH and decreasing my H plus. So the concentration of hydronium ions must be decreasing, but by a factor of what? I'm going to go back up to my pH scale and see that to get from water with a pH of 7 to egg whites at a pH of 9, I had to make 2 jumps, each worth a factor of 10. So 10 times 10 means that egg whites are 100 times more basic, or they have 100 times less H plus than distilled water. So the key thing to remember here is keeping straight on your pH scale. Your low numbers are acids, your high numbers are bases, 7 is your neutral cutoff. When you make a jump on the pH scale, you're doing a 10 times increase or decrease in H+, depending on which way you are moving. So keep that in mind as you work through some problems on the pH scale.